All right, and so now after seeing some examples of mine about how we can do a testing hypothesis problem on those hypotheses about a population proportion value, let's now make some general conclusion here. And so we can formulate a formal order of the steps so that we can carry out any times we're doing a testing hypothesis problem. So from the various examples that I have shown, we recognize the following cases. It's all back to looking at the hypothesis right after we have identified the hypothesis. So the null hypothesis will always be saying a statement as following. The value of P is claimed to be equal to some P sub 0 value. So this value here is a value that our null hypothesis is claiming that the population proportion equals to this claimed value. And then in one case, the alternative hypothesis will read P is less than the value claimed in the null hypothesis. In this case right here, we regard to our test as a left tail test, or in another way of saying, the test we're doing here as soon as we identify the alternative hypothesis that states P is less than the value P sub 0 claimed in the null hypothesis, the test itself is regarded as the left tail test. As another case, our null hypothesis reads P equals P sub 0, some value being stated for the population proportion. Then in this case, the alternative hypothesis can read P is greater than P sub 0. This is another case among our tests when we're doing testing a hypothesis about the population proportion. When the alternative hypothesis is stating that P should be greater than the value that's claimed, we regard to the test we're doing here currently as the right tail test. And there is another case that, aside from the null hypothesis, which again states P equals to a claimed value P sub 0, the alternative hypothesis in this test here may say that P is other than or not equal to P sub 0, the value that's claimed in the null hypothesis. This case is where we refer to our test as a two-tail test. And so identifying the two hypotheses, again, is always the first step in any of the testing hypothesis problem here. We got to be able to identify what H sub 0 is saying, the null hypothesis is saying, and as well as being able to identify the H sub 0, the alternative hypothesis H sub 1. And after successfully identifying the two hypotheses and identify our type of test that we're doing, the following steps are general for any testing hypothesis problem about a population proportion value. After identifying the two hypotheses, we will always list our given sampling information, which includes the sample size and our sample proportion value. And the sample proportion value is usually calculated by the successive count x over the sample size. But now this step is not critically required. The step that is more critically required, is more strictly required, is the following step. That is general in any one of the case, in any one of the three tests that we're doing, either left tail, right tail, or two-tail test. We must multiply our given sample size with p sub 0 and check to see if this product is a number that's greater than or equal to 10. And also we must multiply our sample size with 1 minus p sub 0, the value that's claimed in the null hypothesis for our population proportion. We must also make sure that our sample size after multiply with this 1 minus p sub 0 must be also a value greater than or equal to 10. These are the two requirements in order to move on to the later steps of the problem. As soon as our sample size has passed the two requirements together. So notice how I use the and right here. We have to have this sample size past this requirement and also pass that other requirement by making sure the sample size after this product right here will all be greater than or equal to 10. And once we these are the two requirements that guarantee our sample size or our sample at this size will be a working sample and be good for us in order to move on to the next step. And once we have our sample size past the two requirements in order to move on with the test, then we can see from the examples that we can start calculating the z-score of our sample proportion by doing the following setup right here. The p sub 0, which is our sample proportion. We are going to subtract the center of the sampling distribution bell curve, mu p hat. And we will divide that difference here by sigma p hat. And this is what to know. The mu sigma p hat will always equal to the p sub 0 that is claimed in the null hypothesis. The sigma p hat that we are doing in our calculation of the z-score can be found by doing the following mathematical operation. We take square root of p sub 0 times 1 minus p sub 0 in parentheses. So as a reminder again, this p sub 0 is the value that's stated in the null hypothesis. And this product here is divided by the sample size, and everything is taken inside a square root. Once this step is done, calculating the z-score for our sample, the next step is to set up the calculation for the p-value. When our test is decided from the beginning to be a left-tail test, we will calculate the p-value by setting up the following calculation. We find a probability where among all sample proportions at size n given in the problem. So again, we want to find the probability that among all sample proportions at size n, we would find one that is less than or equal to the specific sample proportion that we have in our problem. So this is a lowercase p hat that came out from our sample. And this is just a general random variable that represents all sample proportions at the same sample size here, where our sample is one among the infinitely many others. And this is where we can put our problem on a bell curve and calculate the probability as stated here as the probability on where we find z-score less than or equal to the z-score for our p-hats that we have found, that we have calculated previously. And in order to obtain this probability, we run our, if we are using the TI-83 or 84 calculator, we run the normal CDF command, where we take a low end being negative 1E99 and the high end, the upper end being our z-score value, and default at 0 and 1 for mu and sigma for our normal CDF command. So this is how we calculate our p-value when our test is a left tail test. Now when our test is a right tail test, we will also need to calculate the p-value for our sample. But the p-value will be set up as following. The p-value for a right tail test is calculated as the probability where we find a sample proportion at size n being greater than or equal to the specific sample proportion that we have in our sample. So this is again our sample. This is a random variable that represents any other sample proportions at the same sample size with the one we have. Notice how the inequality agrees with the inequality in the alternative hypothesis. The same here in the case of a left tail. The inequality in our probability calculation agrees with this inequality in the alternative hypothesis. Calculating this probability will be the same as calculating the probability where we find a z-score greater than or equal to the z-score we have found for our sample proportion, the z sub p hats that we have calculated previously. And now calculating this probability is just a matter of running the normal CDF command on a TI-83 or 84 calculator or some equivalent technology. But this time I am going to run this normal CDF command taking the z-score we calculated here as the low end, where upper end is going to be positive 1E99, and it's going to be comma 0, comma 1 for these two values right here, mu and sigma on our standard normal distribution bell curve. And now when our test is a two-tailed test, calculating p-value must be done a little more cautiously right here. So there are two cases. We will calculate p-value by calculating the probability where our sample proportions or any sample proportion is greater than or equal to the sample value that we've found. Notice how I use the right tail inequality right here and multiply that probability by 2. But we're only doing this if our z-score is a positive z-score. In another case, we will calculate p-value as the probability where we find a sample proportion at size n less than or equal to the value we have obtained, the value of the sample proportion we have in our problem, and multiply that probability by 2. But we use this left-hand inequality in our probability statements if the z-score we have calculated from this step is a negative z-score. So this is what we need to pay attention to when anytime we are calculating p-value for a two-tailed test. And anytime we're doing a two-tailed test, make sure we multiply the probability, either a right tail probability or the left tail probability by 2. And that's why I wrote that in red ink here. Now that we have done calculating the p-value successfully, that which depends on the different cases of our test. This is how we're doing calculating. This is how we're calculating p-value for left tail. This is how we're calculating p-value for right tail, and this is how we're calculating the p-value for a two-tailed test. Now, once we have finished calculating the p-value for our test, then from what we have seen throughout the examples, p-value, our final p-value must be compared. All right, p-value must be compared with the given significance level. And significance level, symbolically, we use the symbol alpha, lowercase letter a, lowercase Greek letter a, alpha. This is for significance level. And so, by comparing our p-value with significance level alpha, then we will lead to the following conclusion. If our p-value is strictly less than the given alpha, our significance level, then we can come to the following conclusion. Our sample shows strong evidence. Or for short, we have strong evidence right from our sample. Otherwise, if the p-value after comparisons with the given significance level shows greater than or equal the significance level, then we come to the following conclusion. Our sample is not showing strong evidence. Or for short, I'm just saying our conclusion here is we're not having strong evidence. And having strong evidence is to reject H sub 0 or to accept or to support H1. And the same way right here, not having strong evidence means we will fail to reject H sub 0 or we fail to support H1. And so this is the summary of all the highlighted steps in this certain order anytime we are testing a hypothesis about a population proportion value.